All right, this lecture is going to finish off chapter 5, and it's looking at the assignment model. Now, the assignment model is solved by something called the Hungarian method, and it is a variant of the transportation problem we've already seen with some extra conditions on it. With those extra conditions, it means that we have a more efficient way of solving the problem. So this is designed to solve problems like this, where you have a group of applicants applying for a group of jobs with known costs for each combination. So the key thing here is that you can think of it as a transportation problem where all of the supply and demand is equal to 1. So for instance, a repair shop has 3 technicians available and 3 repair jobs, and you want to assign a single technician to a single job. And there's different costs for it. So the question is, how can you do it for the cheapest amount? How can the applicants be assigned to the costs to minimize the total cost? That's an assignment problem. As I said, it's really a transportation problem where you have a single unit of supply and a single unit of demand at each center. So if you were to take that problem and write it out in terms of a linear program, this is what you get. So what you are going to be dealing with are Boolean variables. So let xij equal to 1 if applicant 1 gets a job or 0 otherwise. So that's what you're really looking for. So if applicant 2 gets job 3, x23 is equal to 0. When you're doing that, what you're doing is you're trying to minimize the sum of all those costs, and then that xij equal to 0 means that you don't incur those costs. So you can see how this gives you the total cost of only the assignments that you've made. Subject to, this is every column has to sum up to 1. So in other words, only one person gets assigned to each job. Sorry, that's every row. So every person gets assigned to only one job. And the last ones are the column conditions. For every column means that at most one person is assigned to each job. That's exactly what we're looking for. And then we can say that xij is greater than or equal to 0, and it's integral. So in other words, it's going to be 0, 1, 2, 3, 4, 5, and so on. But because of the conditions that the sum of a whole bunch of these numbers is no more than 1, that means the only option is it's going to be 0 or 1. So that's the linear program for this type of problem. Now, the fact that it's integral, in the next chapter we're going to be seeing integral programming. But for now, we're going to see a way to solve this particular problem using the Hungarian method. And here is the algorithm for it. So when you have that matrix of all the costs, the way we saw in the first slide, first thing you're going to do is you're going to look at every row and subtract the largest number from, or the smallest number from every number in that row. Once you do that, you're going to do the same thing with the columns. You're then going to take every column, find the smallest number in that column. It may be 0, but subtract that from every number in that column. Then what we're going to do is we are going to find the minimum number of lines that cover all the zeros. Now, this is the trickiest part of this problem, especially when you have large matrices. You have to find the minimum number of lines to cover all of the zeros. If that's equal to n, in other words, if the number of lines is equal to the number of rows in the matrix, then you have a solution from the tableau. If it isn't, in other words, if you need less lines, you have to continue. You have to make an adjustment. And what do you do there? You find the lowest uncovered number, subtract that from all the uncovered numbers, add that to the intersection of all your lines, and then try again with drawing your lines. So let's take a look at this in practice. So here is the matrix for the problem we just saw, and we step through all of the steps. So first step is look at every row And from that row, you subtract the smallest number. So row 1, the smallest number is 4. You subtract 4 from everything in there. You end up with 0, 2, 4. Do the same for the second row and the third row. So you're subtracting the smallest number from every element in that row. Next step, you take a look at the columns. First column has all zeros. We aren't going to do anything with it. Second column is 2, 1, 4. 1 is the smallest number. Subtract 1 from everything in there. You end up with 1, 0, 3. Fourth column, again, you have a 0 in there, so you aren't going to do anything. So now we're at this stage where we have what's called our column reduced matrix. First one is called a row reduced matrix. Don't get the terminology mixed up with row reduced in terms of linear algebra. We call it a row reduced matrix. The second one we call a column reduced matrix. So once you have your column reduced matrix, what you're going to do is you're going to find the minimum number of lines required to cover up all the zeros. So in this case, if you put a line there and you put a line across there, as are shown in here, you've got all of the zeros covered up with just 2 lines. Since you can do it in 2 lines, you're not done. So now you have to do the final step where you find the smallest uncovered number and subtract it from all the uncovered numbers. So in this case, we have a 1. So what we're going to do is we're going to subtract 1 from all the uncovered numbers. So that'll be from that 1, from the 4, from the 2, and from the 3. And then you look at your lines. Every place you have an intersection of a horizontal and vertical line, in this case there's only 1 spot, you add it there. So you can see that 0 becomes a 1. All the other numbers, you subtract 1 from them, and now you repeat. Find the number of lines needed to cover all the zeros. Well, in this case, you need 3 lines. This isn't the only 3 lines that can do it, but you're just looking at the minimum. 3 lines is the smallest number of lines that you need to cover all of those zeros. That means you're done. So now what do? You pick out of here 1 0 for every row so that every column also has a 0 in it. And here you're going to find quite often with the Hungarian method, you are going to have multiple solutions. So it's not unusual to have multiple solutions. In this case, if we take that 0, that 0, and that 0, that is our minimum, or that is a 0 for every row and every column, and that is our minimum cost. Take those 3 numbers from your original matrix. In the original matrix, that is a 6, a 2, and a 5 right there. That gives us our minimum cost. That's the Hungarian method. When you're going through the Hungarian method, the hardest thing to do is to find the minimum number of lines, especially if you have a large matrix. That is computationally the hardest element in here. But it is a very efficient method for solving assignment problems. And this just repeats that to find the solution, pick out a set of zeros in the final tableau such that every row and column has a 0. So another example. So a dispatcher with 4 cars to transport people, 4 requests for cars. Look at the map to find the distances the cars are and how could the cars be assigned to pick up each person. Notice that this is now starting to get into something that Uber or Lyft might be using in the background. So what do we do for this? Well, the first step is subtract the smallest number from each row. So that gives us all zeros across the top. It gives us 0, 2, 4, and 6, and so on. And there's our row reduced. Now the second step is to give the column reduced. Note here though that every column actually has a 0. So the column reduction is not going to give us anything extra. So the column reduced is the same as the row reduced in this problem. So now we're going to cover up all the zeros with the minimum number of lines. So we can do it with that and with that. And now we look in here and find the smallest non-covered, and we subtract that from everything and add it to the intersections. So what do we end up with? We end up with 1, 0, 0, 0 across the top. And that's a 1, 2. So there is our another iteration. Now look at how many lines you need to cover it. We can cover it with that, that, and that. Now we have 3 lines. We're still not there. We need 4 lines. So we are going to once again do the row reduction or do the subtraction. There's our smallest number. What do we get now? 1. Oh, sorry. That one is actually at an intersection. So it becomes 2, 0, 0, 0. And just continue along, subtracting 1 from every number that is not covered and adding 1 to everything that is an intersection. Now we take a look at it and we try to cover again with the minimum number of lines. What can we do here? I'll take a look. We can still do this with 3 lines. So we do it again. Now for the third iteration, we are going to get this, and I'm running out of room here. We have a 1 that is the smallest number again. Now, if we try to cover this in 3 lines, we can't. We need 4 lines to cover it. So now we're done. So now we have to find a number in every row and every column, 4 numbers. That's a 0. So where do we have that? Well, we have to take that one. We'll have to take that one. And here we have a choice for the next couple. So I can take those 2, and that gives me my solution. So going back to my original, my solution is here, 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 and here. There is my minimum cost. And notice in this case, it took multiple iterations to find it, where we had to find the number of covering lines. So if we take this problem, let's take a look at it a little bit theoretically. If we take this problem and write it out, what do we have in general? Well, I wrote out a specific problem at the start, but if we just have a general n by n assignment problem, our problem again is we're going to use Boolean variables. So the xij's are equal to 1 or 0. Our matrix of costs is the Cij matrix. So we're trying to minimize the sum of all costs times either 0 if it's not used or 1 if it is used. So that's our general problem. Subject to. There's our constraints. So our entire linear program is an integer program written that way. So now why does this Hungarian method work? Well, the first 2 things that we have is saying, let's subtract a number from a row, and then what we get remaining, subtract a number from a column. Why does that work? So the first 2 steps say to subtract something from every row and then subtract something from every column. So let's take that first step. Let's say that I'm subtracting from every row the number pj. So pj is subtracted from every number in row J. So now what does this mean? You take that row and yourCij's in that entire row becomes Cij minus Pj. So that Pj is subtracted from every element in that row. So that means we're now maximizing this because we've changed ourCij's. So this is really a Z prime. But now remember Pj is just a number. And so you can break that up to your original minus Pj xj. There's going to be an all of them. But that is the same number repeated n times, and only one of those is a 1. Everything else is 0. So you get P1 times 0, P2 times 0, P3 times 1, and then so on. There's only one of them that remains in there. So you are subtracting just the Pj, and then you're doing it for every row in your matrix. So what are you doing? You have changed your optimal function, or your objective function, to what it originally was minus a constant. And that constant is the sum of all the numbers that you've subtracted. So if you think about what the solution is going to be the exact same because your restrictions don't change. TheCij's don't matter in there. The only thing that changes in your new function is that you are subtracting a constant from your objective function, which of course does not change the solution of your variables. So steps 1 and 2 do not change your solution. Step 3, you should be able to see how if you can take 1, 0 from every row and column, that it gives you your solution. The reason for the adjustment with step 4, that's more getting into the dual, and it is something called complementary slackness that we're going to deal with later. So this should give you an idea why the first 2 steps give you the same problem. All right, thanks very much.